Today will be Umberto Hryniewicz from Aachen. He will speak about the interplay between asymptotic cycles and holomorphic curves.
Thank you. First of all, thank the organizers for the invitation. It's a great privilege to speak here. So I will talk a bit about a certain topic which is recurrent in my research interests, which is that of global surface of section. So the basic object of study is flow on a closed connected oriented three-manifold M. And we would like to explore the possibility of reduction of this flow in dimension 3 to a discrete system dimension 2. Okay, so let me just make one definition. A global surface of section. I'm going to abbreviate GSS because I write this many times. Is for phi t is an embedded compact surface such that the following holds. So first of all, the boundary consists of periodic orbits, but it could be empty. So in principle, also allowing this possibility. Yes, sorry. Thank you. So the flow is transverse to the interior. And so for every point in M, there are times positive and negative, such that if you flow this point, for these times you are pointing sigma. So the picture to keep in mind looks more or less like this. I mean, you have a certain surface. Let's say, let me draw a simple picture where you have only one orbit, only one boundary component. So you have, say, a flow in S3, then you have this periodic orbit, gamma, and it spans. So the surface could be a disk looking like this, and then the trajectories for every point you flow back, or if you flow forward, you are hitting the surface. So this would be the phi t minus of x, and this would be phi t plus of x. And then you can, using this, when you find such an object, you can reduce the study of the dynamical properties of this flow to the return map to this global surface of section. I mean, you can define the return time by saying that this is the infimum of all times positive such that the point returns to the surface. By this transversality assumption, this is a smooth map. And by assumption C, this is finite number. And then you can define the return time, the return map by this formula. So, and then periodic orbits of the flow correspond to periodic orbits of this map. Invariant sets of the flow correspond to invariant sets of this map, and so on. And every dynamical object of this flow corresponds to a certain dynamical object of this map. All right. So the most, for me, the prototypical example of result was proved around 1927. It states that if you have a Riemannian metric on the two-sphere and the curvature is positive, then every time you see an embedded closed geodesic, so gamma embedded closed geodesic, you can actually obtain, associated to such an orbit, you can obtain a nullus-like global surface of section for the geodesic flow, which is a flow on the unit tangent bundle, which is a three-manifold, diffeomorphic to RP3. So you can choose a hemisphere, and then every point here you consider the unit vectors pointing towards this hemisphere. Then you go around to this point to get an embedded annulus in the unit sphere bundle, and this annulus denoted by A gamma is a global surface section. Okay. So that there is something mysterious about this assumption. This is somehow taking care, this assumption is implying very strong dynamical consequences. You have this annulus, and every single trajectory is going to hit it. So it's a very nice situation for the dynamicist, because you look at the object, and then you see that the curvature is positive, and all of a sudden you have lots and lots of information about the flow. So then, then you can study this flow by the return map to this annulus, and this map is actually going to preserve a certain area form, and then, then there is a lot of machinery that you can use for studying maps on the annulus, which is great. All right. So it's a bit of challenge to understand what's going on here. So in this picture, just means that being a global surface section, for the statement that A gamma is a global surface section, just means that every trajectory, every geodesic is going to flip hemispheres infinitely often in the future and the past. Okay. So let's then try to study the general case. Here's we're talking about specific flow, geodesic flow on S2, and we're making specific assumptions. And let's try to understand the question of when a certain collection of periodic orbits will bound the global surface section. Just one comment. Maybe somebody might complain that this definition is a bit restrictive because, I'm asking too much that if I ask that the surface is embedded. But you can define rational versions of this notion. One can ask sigma to be embedded up to the boundary, because not up to the boundary, embedded in the interior, but then at the boundary, you get a certain covering of the periodic orbits, and you might call them rational global surface of section. Maybe they're more appropriate. An example of such a rational thing would be when the curvature is 1/4 pinched here. Then if you have this better pinching condition, you can, for such a closed geodesic gamma, you can go twice around it, and then in the unit sphere bundle, this will be contractible. Actually, it will be unknotted, and there will be a disk, and this disk will also be a global surface of section. So in this case here, you get this rational global surface of section. All right, but then let's study this problem. So consider a link. That's right. So consider a link. Now I'm back to the general setup here. I'm considering a flow on a 3-manifold and nothing else. I'm just orienting the 3-manifold. I'm assuming it's orientable and fixed in orientation. Consider a link consisting of periodic orbits or the empty set. Then we can consider the set of flow invariant Borel probability measures on the complement. And then once we fix such a measure, then, well, then mu almost every point is recurrent. Right, so for mu almost every point, you find sequences of numbers such that the flow almost returns. Right. So I mean, you have consider large numbers, then you start from such a recurrent point. For infinitely many large values of the flow time, you're gonna come very close. So T large. And then what you can do is you can consider a loop which obtained by such long trajectories which almost close up, and then you close it up with a short path, right? Short path from phi t to x. Right. Of course, this is very unambiguous. I'm not saying which time it is. I'm just saying it's a time where this endpoint is very near the initial point, and I'm not saying exactly how do I choose. I'm just saying it's short. It doesn't matter too much. I mean, just keep in mind that this is an ambiguous notation. Okay. So then the one lemma that one can prove is the following. So for every pair mu y consisting of such an invariant probability measure and cohomology class in the complement, say with real coefficients, there exists an integrable function with the following property. For almost every point, the value that you obtain by averaging time what you get from that loop by hitting with this cohomology class is convergent and is equal to this. This holds for all. For mu almost every point x. Meaning that, what do I mean by this? I mean that every time, so for mu almost every point, the following happens. Every time I choose a sequence of numbers, Tn, converging to infinity, such that phi Tn converges to x, and then I close it up with a short path, I get a loop, I hit with this degree 1 cohomology class, I get a number, I average in time, this limit is converging. And then, with this at hand, it's interesting to define intersection number. Maybe intersection number for, well, it's a good terminology, but also a bad terminology, because it's a real value intersection number. It's kind of, so you can define the intersection number, which is just the integral of this function. So let's say so it's the intersection number of the invariant measure with the cohomology class. So why does one want to call it an intersection number? Because, for instance, if y would be Poincare dual to a surface whose boundary is in L, right? So say you take a cohomology, degree 2 homology class modulo L, and you take the dual class, right? And then this would be an average intersection number of that surface. More precisely, in the special case where mu comes from a periodic orbit, and y comes from, when y is the Poincare dual of such a homology class degree 2 modulo L, this would be really 1 over the period times the actual intersection number of the periodic orbit with the surface. So that's a reason to call it intersection number. All right. So then you see that if L is going to bound the global surface section, it's got to be true that the class dual to this global surface section will have to intersect positively all invariant measures, because invariant measures are going around like this, so, right? Because if it's a global surface section, trajectories are going around, so you're picking up intersection number. So it's looking like these intersection numbers being positive, it's a necessary condition for, with a class which is Poincare dual to a relative class to the link, then this has got to be a necessary condition. All right. Then you can also consider rotation numbers. Let's say you have one of these periodic orbits, and then you take a tubular neighborhood of such an orbit. So here is gamma. Let's say this is T, where I'm choosing this neighborhood, these coordinates in such a way that on the periodic orbit, the vector field is dt, and then I'm going to call this coordinate here theta, and I'm going to call this coordinate here r. Say. And I'm asking that dt dr d theta is positive. So if you choose such coordinates on a tubular neighborhood of the periodic orbit, Then, so here T is the period. Then you can write your cohomology class, let's call this N. Your cohomology class as P dt plus Q d theta. And then you might want to define the rotation number with respect to y as such a limit. Where by theta of t I mean a lift of the argument of the transverse linearized flow, right? I mean, I take a little vector here, and I go around, and I start measuring. So the linearized flow carries this little vector, and then you see in these coordinates, you see how much this angle theta is changing, and then take this limit. This is really just the rotation number of the lift specified by this linearized flow and the coordinates of the return map on the transverse linearized dynamic on this circle of rays. Just this rotation number. And then fact is that it's independent of choice of coordinates. Now, if you see, if let's say you have a global surface section, and y is the dual class, and you choose coordinates in such a way that the global surface section is looking like this. Just say theta is equal to constant. Then, well, then this, the flow nearby is going transversely. Then you pass through the limit as you approach the orbit to get also positivity of these limits here, right? I mean, if you take so if you take coordinates in such a way that the global surface sections look like this, and y is the the dual class, then you just get p equals 0, q to plus or minus 1, depending on the orientation, and then you get a plus or minus 1, a plus or minus rotation number. And if it's to be a global surface section, then it should be positive. The rotation number should be positive number because the trajectories near the periodic orbits want to hit the surface. So it's looking like a rotation number being positive is also a necessary condition. And then one can state a certain refinement of results of a result due to David Fried. But it's many new aspects on the statement which I'm going to make. So you fix B. Suppose L is no homologous. Suppose there exists B integer valued relative homology class induced by a cipher surface sigma for L. Okay. Then you consider the following assertions. There exists a global surface of section bounded by L, representing the class B. By the way, I should say that every time I talk about so the reason why I assume the ambient manifold is oriented is because I want my global surface of section to inherit a natural orientation because the flow co-orients the surface. So I use the ambient orientation to orient the surface. So that's what I mean. So then this makes sense, right? Because my global surface of section is oriented by the co-orientation of the flow and the ambient orientation. So second statement is there exists an open book decomposition bounded by L, whose pages are global surface section for the flow representing the class B. And the third item is stating that, so I'm going to note by B star the one, so the degree 1 cohomology class dual to B, but forget about the Z coefficients. We use it, we make it, think of it with real coefficients, doesn't matter. So this rotation number is positive for all periodic orbits on gamma, and the intersection number of the dual class with mu is positive for all mu. And the theorem then says that roughly these three statements are equivalent. So this chain of implications always holds. And 1 implies 3 infinity generically. So the infinity generic assumption here is that if gamma, so if you have such an orbit with 0 rotation number, then this orbit has to be hyperbolic. Okay. So then you get a statement with which you can start studying the general case, any flow and any three-manifold. And then the picture is clear that, so what's the real hard tasks is this one. And the way, well, it's clear that, so that's the hard part. That's what should be clear, more or less, from the definitions, because things are going around. You have to link, right? But that's actually the only, so the easier statement is the one that's thought was a bit subtle, a bit more subtle also because it's not true in general. Anyway. So there is something about Birkhoff's result. So remember Birkhoff's result. You have this, this pair of periodic orbits, which are the embedded, given by the velocity vectors of this embedded closed geodesic. And somehow the positivity of the curvature is taking care of this assumption here. So you have information, all invariant measures, just from positivity of the curvature, which is a bit surprising. And that's what I would like to investigate. Any questions about statements, definitions? All right. So what's the usual criticism about this statement? Is that one, one never checks three. So if you never check the hypothesis, how are you going to apply? Because you have to check, you have to know all the invariant measures, right? So that's pretty impossible task in general. Second criticism is one that I make, is holomorphic curves can do much better for Hebb flows in 3D. And my goal, well, one of the goals of this talk is to refute criticism 1 and reinforce criticism number 2. So that's what I hope to do. So this means I would like to make I would like to check this hypothesis a bit more efficiently. So one example of statement where one can see that holomorphic curves can do much better is, for instance, this one. On a convex, so it's on a strictly convex energy level, inside R4, and I mean compact and smooth. A periodic orbit gamma. I don't fix the parameterization of the flow, I just think of characteristic flow. Periodic gamma, orbit gamma bounds a disk-like GS, global surface section, GSS, if and only if gamma is unknotted and the self-linking number of gamma is -1. So this is a bit like in Birchhoff's statement where you have some kind of positivity of the curvature in some sense, and you have an orbit, you don't have to check anything about the dynamics. You just look at the orbit, then check, orbit is unknotted? Yes, nothing to do with the dynamics. Does the orbit have self-linking -1? If yes, then you get all linking information, all invariant measures in the complement, you get the global surface section, and so on. So there's got to be something, so somehow this convexity assumption is taking care of knowledge about all invariant measures in the complement. Okay. All right. So maybe I don't erase. Okay. So really the result I'd like to explain today is the following. This is going to work with Pedro Salomão, and the result states the following. Suppose you have a collection, finite collection, of periodic orbits. Suppose you have a partition of such periodic orbits. And suppose we're given also an oriented Cypher surface. And by the way, here I have to say, induced by a Cypher surface, I have to assume, of course, it's oriented, otherwise it doesn't make sense. Suppose I have an oriented Cypher surface, sigma, and the boundary of the Cypher surface is equal to this collection of periodic orbits. And then I would like to make a statement where I can check all this stuff if you know something about these orbits. Well, actually, this statement is still going to be, or the assumptions are going to be still hard to check in general, but then later I'd like to use this statement to actually check them and get a global surface new global surface section. So That's the plan. Assume that for every I, there exists a strong, I didn't say what this is. There's a strong global surface section, SI, with boundary equal to the collection of periodic orbits in gamma I. And so that's one thing. Assume also that the SI and sigma
What do you mean by strong?
sorry?
What do you mean by strong?
Yeah, so strong, let me just say that here. Strong means that the return time function, so here, so you have tau I, which is the return time function to this global surface section SI, is bounded from above. That's what I mean by strong. I must say that every time you get a global surface section by applying this result, actually you get a strong one, because convexity implies that the Conley-Zinder index, well, the Conley-Zinder index being, the convexity implies dynamical convexity, which means that the Conley-Zinder index is at least equal to 3 for all periodic orbits. And this translates into a certain twist of the linearized dynamics along each orbit, which forces then, once you get a global surface section, this thing actually comes from a holomorphic curve. Then you can use this fact and this strong twist given by convexity to say that actually the return return times are bounded from above. So it doesn't, yeah, okay. So in principle, it could be that there is a global surface section where the return time explodes as you approach the boundary. So the second assumption here is that this these guys actually orient each gamma in the same manner. And sigma minus the sum of the SIs is torsion class in H2. Okay? Because there is something about, like when you talk about holomorphic curves, you always talk about positive punctures, negative punctures. Here's the same thing. I mean, you have a global surface section, the flow and the ambient orientation. The flow and the ambient orientation orient the global surface section might be that if you look at the boundary orientation at certain periodic orbit, this might coincide or not coincide with the flow orientation. This would be like positive and negative punctures for a holomorphic curve. All right, so then there exists a global surface section S such that well, first of all, the boundary is all the orbits. And second of all, the class is equal to the class of the initial given cipher surface. So you represent that class. So this statement is just saying that once you have a few global surface sections, they might proliferate and give more and more global surfaces of section. And the good thing about this is that, well, first is for a general flow, not rip flow. I mean, no assumptions here. And second is that these methods, which are used to prove the previous result and this one, they don't see any genus problems. I mean, if you want to work with holomorphic curves, when you start working holomorphic curves with genus, you already run into nightmare, compactness nightmare, because breaking can happen in such in ways which are not directly related to periodic orbits, so you never know how to use the dynamics to control, to produce compactness. And here there is no, genus is not an issue here. So, and then there is one, okay. So then there is this picture. So the motivation to try to prove results like this is, to me, well, come from very specific systems like geodesic flows, or systems coming from celestial mechanics like the planar circular restricted three-body problem, where there are classical results of Poincaré and Conley asserting that for subcritical energy levels, if the mass ratio is concentrated, almost all concentrated near one of the primaries, and the satellites moving near to that heavy primary, you can obtain annulus-like global surface section, which that's what motivated Poincaré to state the Poincaré-Birkhoff theorem. Or you also have results of Conley, the pre-thesis of Conley under Moser, stating that if you go for energies very close to minus infinity, you have such a situation as well, where you have two orbits. After certain regularization procedure, you have two orbits spanning an annulus-like global surface section. And after holomorphic curve, after the work of Hofstadter-Zander, we understand well how to get disk-like global surface section, but different kinds of sections are still not so clear. But now with this result, we can improve a bit the situation on these classical systems. For instance, you can say that, so just one corollary. So if you have dynamically convex Hebb flow on S3, and a pair of orbits forming a Hopf-Link, then the union of these two guys, they span an annulus-like global surface section, which is now, we would like to, second step now is to try to actually apply this result for general cases of the planar circular three-body problem. Of course, there is an issue of checking dynamical convexity. Maybe it's not always true, but then that's a tool to try to use in that problem. Okay, so the recover classical situations. Poincaré, Conley, etc.
Is the result for general flows or general rate flows?
The results for general flows. Yes.
General flows.
Yes. But why is this a corollary of this? Because well, these guys, by that result, these two orbits, they span this global surface section. So then you can apply this guy here and get the annulus-like. But then, that's a special case of another corollary, which states that if you have any link, so again, in the context of of a dynamically convex Hebb flow on S3, if you have a bunch of periodic orbits, and each gamma I is unknotted and self-linking -1. I mean, this is just saying that it's transversely isotopic to a Hopf fiber. Nothing, just fancy way of saying this. Then, again, the collection of all these guys also bounds a global surface of section. And now, for instance, you can see that, well, if you actually take a bunch of periodic orbits as you see them in the Hopf fibration, and if there are many, the cipher genus is actually big. The cipher genus of a collection of Hopf fibers, as you see them in the Hopf fibration, when you take many, many of them, this genus explodes. So this global surface of section, they are really with genus. There is an interesting result, an interesting preprint of due to Albers, Geiges, and Zemisch in the archive, where they study genus of these links. But okay, so that's these are results which are completely nailed down. The proof is I can attest for completeness of the proof. Now I want to explain a bit what I would like to do beyond such applications. Still have 10 minutes. So one question which I think is fascinating is, what structure theorems can one prove for zero entropy Hebb flows. I mean, there are many structure theorems for zero entropy dynamical systems. I mean, the zero entropy is this mysterious class of systems, and they are, of course, yes, topological entropy. And in some sense, one question, which is very much advertised by Katok, is that whether, how close these things are from being integrable in some sense. So it's a tough one. Well, Barney Bramham have results on this direction, in the direction of proving rigidity in some sense. And well, so one result which I would like to, one nice result, which is kind of recent, is due to Patrice Lecalvez and Fabio Tao, where they study zero entropy systems in the context of surface homomorphism, and they they really prove a nice structure of theorems. Basically, you decompose the system into a bunch of rotations in annuli, basically, up to excluding a certain invariant set. Okay. So more people. Okay. So the question in this context here, in the context of dynamically convex Hebb flows on the tree-sphere, so this question incarnates in a more specific question. I mean, what kind of links can appear as periodic orbits, as links of periodic orbits? For a zero entropy dynamically convex Hebb flow on S3. Okay. So, and then even a special case, one can consider, one can try to, so in general this question probably also a bit out of hand, but one can then think of a more specific question about links consist of periodic orbits for zero entropy dynamic convex Hebb flows in the tree-sphere, all of which are transversely isotopic to a Hebb fiber, all of which are not at self-linking -1. And then so what is your favorite zero entropy Hebb flow on the tree-sphere? I mean, the integrable ones, right? And then if you force dynamical convexity, then the imagination already runs short very, very quickly. I mean, you can think of ellipsoids, basically. So in ellipsoids, what can you see? You have Hopf links, and then you have also links of torus knot links of the form N1. So unknotted guys, torus links. And then the imagination kind of runs short. I don't know. And then, well, what I'm hoping to prove is that actually you cannot imagine much more. I mean, so the say, congerum would be that's all. I mean, if you're talking about, dynamically convex Hebb flow on S3, then and a bunch of periodic orbits, all of which are knotted self-linking -1, then they appear as you would see them inside, so as periodic orbits of a rational, or of an ellipsoid. It could be rational. Meaning, well, if you have a, say for instance, they could appear as a bunch of hop fibers as you see them in the hop fibration. That's okay. That's one possibility. They could appear, for instance, if your ellipsoid here is a 2-1 ellipsoid, they could appear as a hop link plus a few 2-1 torus knots around the components of the link. And if the ellipsoid is, so the only way you can get a knot of link -1 is if you get a torus knot, a torus link of this kind, and then you only allow to see ellipsoids of the form E and 1. So basically, if you see a bunch of hop fibers and they are not very, very carefully placed, entropy is positive. And the reason is that, well, individually, each one of them is bounding and loose like global surface section, so you can apply the other result. So collectively, they bound the global surface section. And then once you get, yes, so once the link you see is not exactly one of those, you get that the isotopic class of the return map is not going to be in the class of periodic guys, it's going to be in the class of pseudo-anosov map, and then you're forced in topological entropy. That's the proof. That will be the strategy of proving this structure result for zero entropy systems in S3. So basically, yeah, we just try to get information of the isotopic class of return map in terms of the topology of the link. That's the mechanism. And the only way, I mean, you need a two-dimensional reduction because in 3 dimensions, you don't have such technology. In 2 dimensions, things are much more well developed. Okay, so maybe I'll stop here. Thank you.